Today's seminar is Alessandro Caritenuto from Prague, the Charles University, who will be speaking about a Borel-Weil theorem for irreducible quantum-like manifolds.
Thank you for the presentation, Ren. And I am happy to be here basically after 1 year with a live crowd with more than 2 people. And today it will be my pleasure to report on one of our latest work with Freddy and Raymond, that is the proof of the Borel-Weil theorem for irreducible quantum Flagg manifolds. So I think a good point to get started is to review some classical theory. So the classical Borel-Weil theorem is a very important result in classical differential geometry. It was attributed for the first time to Borel and Weil by Serre, by no other than Serre, at the 100 expose of the Bourbaki seminar. And what it claims is that we can realize each reducible representation of any complex semi-simple Lie algebra G as the space of holomorphic sections of a Lamb bundle over a Flagg manifold of G. At this level, we just need to know that a Flagg manifold is some class. Flagg manifolds are a class of homogeneous spaces for the Lie group associated to G. This result is considered a very strong, important foundational result for geometric representation theory. We might even say that it's the first thing that you might want to prove if you want to get started in studying geometric representation theory. That is not other than that line of thought that if we want to look at some class of groups, in particular Lie groups, as geometric objects, we should be able, and in fact we are able, to give a geometric realization of their representation theory. And it's not surprised that this theorem is also the first step to prove other important results that followed. First of all, the Borel-Weil-Bott theorem, or Bott Borel-Weil, or any combination of these 2 names, which is basically a generalization of Borel-Bott or Borel-Weil, I'm sorry, to higher homologies. Then, I list only 3 theorems that follow from Borel-Weil, but the list could be way longer. Anyway, I wanted to point out the result of the result of Kummer's decomposition, that is a decomposition of the tensor product of 2 irreducible finite dimensional representations. And here, what is surprising, I think, is that one can use the Borel-Weil, which is a geometrical theorem in nature, to prove some fundamental results in representation theory. And then we also have Bellinson-Bernstein, which is a very far-reaching generalization of Borel-Weil that deals with the coherent shifts on the Flagg manifold. So if we believe, as we do, in the motto that non-commutative geometry is geometry, it's not surprised that people wanted to give generalization, started to give generalization of the Borel-Weil theorem for a non-commutative setting. Again, I can only give a partial list of the contributions in this direction. And so I gave some notable one, of course. First of all, we have the approach of Anderson, Polo, and Venn that was based on derived homological algebra. Then again, from a purely algebraic point of view, we have the quantum coordinate algebras approach, both of Partial and Wang, and Mimachi, Naomi, and Yamada. Then there have been some proofs of the Borel-Weil theorem that have a more mathematical physics flavor, like the one of Biedermann law, which was based on Q bosons, and here in Prague, the one of Jurčo and Stovček, that was based on a coherent states approach. There has been also a proof in a more system algebraic setting by Gover and Zhang. And finally, let me point out that Kramnitzer and Becklin generalize the Beilinson and Bernstein localization theorem to the quantum setting. Now, why we, as you can say, there is a certain number of proofs of the Borel-Weil, and one might ask why then we bother to prove again a theorem that was already proved. Well, the thing is that in the classical setting, in the classical setting, one has an equivalence between the holomorphic sections. I'm very not good at using this. The holomorphic section of a line bundle over flag manifolds and the Borel invariant section of state line bundle. And very roughly speaking, and very limited to my understanding of these works, all the works above generalize the description given in terms of Borel invariant section, without introducing any notion of holomorphicity, mainly because there was no notion of holomorphicity at the time when these, at the time in which these works were written. So, in more recent years, we as community have got a better understanding of the non-commutative complex geometry of quantum flag manifolds. So now we do have a notion of holomorphicity, and people started to feel confident about the possibility of proving Borel-Weil theorem in its original setting, that is the setting of complex structure. So that's what this other bunch of people did. So the first foundation, the first work was from Beggs and Majid that proved Borel-Weil for the Podre sphere. That is always the first example of quantum flag manifold. Then in a series of, I think, 3 papers, Calcali, Landi, Van Strelico, and Motalderro, sorry, or I mean, various combinations of these 4 names proved the Borel-Weil theorem for the quantum projective spaces, expanding the notion of holomorphic vector bundles. And let me point out that the same notions also appeared in the work of Beggs and Majid on commutative coherent shifts. Finally, together with Colin Bronzinski and Raymond, we proved the Borel-Weil theorem using, for the quantum Grassmannian, using a quasi-triangular representation of the differential calculus of the quantum Grassmannian. In principle, one could apply the same approach for the other irreducible quantum flag manifolds, but as a matter of fact, it will be very difficult, and we had to prove the same result in another way for this more general case. So let me announce what is the theorem that we want to prove today, the quantum Borel-Weil theorem. For any irreducible quantum flag manifolds, the space of holomorphic sections of the case vector bundle over OQ of GOS is a module over UQ of G of highest weight K var Px, where K, where for the simple root alpha x that corresponds to the cross node of our flag manifold, var Px is the corresponding fundamental weight. As we already see, we have to introduce some preliminary material in order to understand this statement, and that's what I will do. Also, I tried to structure this talk in a very self-contained way, so there is a lot that I'm adding under the carpet. There are a lot of technical tools that we need to prove the Borel-Veil theorem, but I will try to present just the structure that we need to understand this statement. So let's start from the first object that I'm quite sure you're pretty familiar with, which is UQ of G, the Drinfeld-Jimbo quantum enveloping algebra of a classical Lie algebra G. So suppose that G is a finite dimensional complex semi-simple Lie algebra of rank L. We fix a Cartan subalgebra H, and we choose a set of simple roots of L simple roots. Then we have an associated Cartan matrix. Then for any real number, Q, we excluding -1, 0, 1, we define the Drinfeld-Jimbo quantized enveloping algebra UQ of G as the associative algebra generated by L sets of elements EI, FI, KI, and KI -1, subject to this bunch of relations plus the quantum star relation that I omitted because there is just as much space on a slide. And so what I want to point out here is not important that you learn these relations right now. What I want to point out is that this is a non-commutative algebra, which is in fact considered as a legitimate non-commutative Q deformation of the enveloping algebra of G. And its non-commutativity highly depends on the Lie theory of G, since the coefficient of the Cartan matrix appear in the relations. And as a matter of fact, UQ of G has the structure of an op algebra. We can put a good coproduct, a good counit, and an antipode. They interact in the right way. And this guy is an op algebra. Fantastic. Then, and we can decide to study, we want to study the representation theory of UQ of G. We might ask what changes with respect to the classical case. The answer is not much. The representation theory of UQ of G is quite well developed, quite well behaved under deformation. So this is just a reminder then of all the notation that we will have in the rest of the talk. So if I denote by P plus the span of the fundamental weights by positive integers, then, and I forgot to say that I denote by P the Z span of the fundamental weight, then okay, let's denote these two guys in this way. And I defined a vector of weight of V inside of the of P in this way. So K acts on V, and I get Q to this power, where this is the Killing form on G. Then for each guy inside the span of the positive span of the fundamental weights, I have a reducible finite dimensional representation of UQ of G. And this is completely defined by the existence of what we call the highest weight vector. That is just the vector which is filled by the simple roots econ EI. And we call any finite direct sum of UQG representation of this kind a type 1 representation. P plus, yeah, P is the Z. So I have here, I have what I call the simple roots, which are basically the I and the phi. And the alpha I are basically the covectors dual to the root. Well, to, not exactly, but at this level, yeah, they are the collectors dual to the simple roots, and I consider the Z greater or equal dimensional span of these guys. And this thing, as I said, classify all the type 1 representation of U of G. So you can just take them as a way to label the representations of our Q-deformed algebra. And this is relevant if we want to introduce the deformation of the coordinate, good deformation of the coordinate function over the Lie group. So if V is any finite dimensional left module over UQ of G, then for every V in, small v inside the capital V and any linear functional over this representation, I can consider this function defined in this way, just evaluation of f on, so it's a function from UQ of G into C. In fact, I just evaluate f on the action of an element in UQ of G on my representation of my vector inside the module. And if we fix V, we can define the coordinate ring as the subspace spanned by this guy. As a matter of fact, this guy is a coalgebra and is contained into the off-dual of UQ of G. Then, if I want to find a op subalgebra, a good op subalgebra of the off-dual, I can take the direct sum over the fundamental, over the positive weights of CV lambda of CV lambda, and we call this guy defined in this way, or QG, is an op algebra, and we call it the quantum coordinate algebra of G, where G is the compact, simple connected, is the compact, simply connected, simple Lie group, which has small g as Lie algebra. So the general consensus about these guys is that they are two different deformations of respectively the enveloping Lie algebra of the classical Lie algebra and of the classical coordinate function or coordinate algebra of G. In fact, for Q that goes to 1, this guy, or QG, is exactly the coordinate algebra of the classical Lie group, while the situation is a bit more nuanced for Q goes to 1 of UQ of G, because it becomes some n-fold cover of the classical enveloping algebra of the Lie algebra G. So as I said, this, as far as topology is concerned, these are some good Q deformations of these two classical objects. In fact, they also meet a crystal algebraic completion that are example of Voronovich compact quantum groups. However, the situation is kind of worse, and it's more controversial if we want to look at some proper quantum geometry on this object. And by this, I mean that if we follow Voronovich's idea of looking for deformed geometries by looking at deformations of the standard Reham complex, things start to get quite bad. So what do I mean by deformation? Is there any question so far?
Of this OQ of G. Yeah, so I was just a bit, I mean, I know you kind of said that as Q goes to 1, this OQ of G reduces to the coordinate algebra. Mm-hmm. So I was just kind of confused where the Lie group suddenly appeared in this
Oh, well, the Lie group you kind of don't see on this level, of course, but it appears because this object is defined as dual, basically as some, yes, is defined as a dual object with respect to UQ of G. So this guy, oh, I'm sorry. This guy is contained inside of the dual of the quantized enveloping algebra of G.
Mm-hmm.
And when Q goes to 1, these guys are actually the coordinate functions over the group.
Oh, okay. I know.
Ah, yes, you have a correspondence between practically you have the correspondence between the Lie algebra and its compact simply connected simple Lie group.
Yeah, fair enough.
So yeah, practically. So in order to look at the form Drang complexes, we might introduce the notion of differential calculus for a non-conductive algebra. So if differential calculus is not other than a differential graded algebra generated in degree 0. That means that it is generated as an algebra by elements A. So I have an exterior derivative here, and as an algebra, this is generated by elements of the form A and B for A and B in omega 0. So in particular, if for some given algebra B, I have that B is equal to omega 0, I say that this is a differential calculus over B. As a matter of fact, we mostly need only first order differential calculus. So a first order differential calculus of an algebra B is given by a pair of a B bimodule and a derivation from B into its bimodule omega 1, such that again, omega 1 is generated as a B module by elements of the form dB. And as I said before, we call D the exterior derivative of the first order differential calculus. Of course, you can always just consider the first component of a differential calculus, and it is a first order differential calculus. But you can go also in the other way. Every first order differential calculus always admits an extension in some suitable sense as differential calculus. Now, a complex structure. We have to introduce complex structure since we wish to describe complex manifolds. A complex structure is not other than a refinement of a differential calculus. So if I have a differential calculus and if I can take the choice of a Z2 grading of omega, such that I have these three very simple compatibility. Also I want a star differential star calculus. You can figure out how the star and the exterior derivative interact. And if the two gradings are compatible in this way, and also the Z grading is compatible with the star structure. And finally, I have that the exterior derivative sends the guys into omega AB into the direct sum of A plus 1B, omega A plus 1B and AB plus 1. I say that I have a complex structure. And yeah, let me introduce just some dictionary here. We call an element of omega AB an MB form. And we denote this to guide the projection over the first factor of the exterior derivative and the projection of on the second factor as del and del bar. As a matter of fact, these are star maps and they satisfy the graded Leibniz rule. Moreover, del square and now moreover del square, sorry, del square to 0 and the anti-commute, meaning that this is a double chain complex. And yes, all of this is a way to abstract the properties of a de Rham complex of a complex manifold. Now, finally, we want this structure to interact with the group structure, because we are studying the formation of a Lie group after all. So we say that the differential calculus is left UQG covariant if omega itself is a left UQG module, and the differential is a UQG module map. And of course, we define similarly right covariance. We can define similarly also B covariance, in fact. And moreover, we say that a complex structure omega is covariant if the Z2 decomposition that I introduced before is a decomposition, sorry, this is badly written, is a decomposition in the category of left UQG modules. We can, as a matter of fact, we have a problem here. We can look for B covariant differential calculi of over OQ of classical dimension, and there is none. That is, we have no good deformation of the de Rham complex over OQ. For quite some time, this was considered a tragedy, and it looked like the theory of Drinfeld-Jimbo deformation of quantum group is not a valuable theory for non-commutative geometry. However, things get better if we decide to study not the differential calculi over the quantum group, but differential calculi over a certain class of homogeneous spaces of the quantum group.
Of classical dimension.
Yes. So remember, as I said, for Q that goes to 1, this is the coordinate algebra of a classical group. A classical group is a complex manifold, and I have a de Rham complex, and the classical dimension is just the dimension of the de Rham complex over G. Is there any questions? Okay. So now we have to introduce the notion of homogeneous state for quantum groups. So if A is an Hopf algebra, we say that a left coideal of A is a quantum homogeneous A space if it is faithfully flat as right B module, and if B plus A is equal to AB plus, and by B plus here, I just mean yes. The intersection of B with the kernel of A. So, okay, if I denote by P of B this quotient, this quotient map, here the quotient A over B plus of A, since we have this equality, is an Hopf algebra, and I can define this coaction. So this equation. And as a matter of fact, it turns out that the coinvariance of H, the coinvariant element of A inside of A with respect to this coaction is given by B. So that's why we call this guy a quantum homogeneous space for the Hopf algebra A. And for UQ of G or OQ of G, we have a nice class of quantum homogeneous spaces that is given by the quantum flag manifolds. So remember that I can describe a simple algebra by using its Dingin diagram. So let's consider, for example, the Dingin diagram of Econen. Each copy of this node, each one of these nodes is basically giving a copy of UQ of SL2. And to define a quantum flag manifold, I just follow this procedure. I erase I cross, I guess, any number of nodes over the Dingin diagram. And I can then consider, I should be careful now, I can now consider the op subalgebra of UQ of G generated in this way. So for each one of these guys, I keep all the K, and I get rid of all the EJ and FJ that are the ones that, okay, of each EJ and FJ that I have crossed. So now this is a sub of algebra of UQ of G. UQ of G as a left coaction of OQ of G, and I can consider the coideal subalgebra of OQ G given by the coinvariance with respect to the coaction of UQ of LS. And yes, so as a matter of fact, of QGLS, this follows from the cosine simplicity of the off-dual of UQLS, UQ of LS, sorry, of the Levy subalgebra. And this guy, as a matter of fact, is an homogeneous space, and we call it the quantum flag manifolds associated to the root system F. So from now on, F is the root system of roots that were not crossed out, and I should remember this. Just a convention, but I always get confused about it. And the guys we're interested in are a certain subset of these quantum flag manifolds. So in particular, it's a subset in which we always have one cross node. And this is the complete list of what we call the reducible quantum flag manifolds. In particular, they could be characterized by the fact that they are the flag manifolds that are also symmetric spaces. So for the AN series, we can cross any of the nodes, and the corresponding flag manifold that I get is a Grassmannian. For the BN series, we are only allowed to cross the first node. For the C series, only the last one. For the series D, we can either cross the first node or any of these two tails. And then I also have two irreducible quantum flag manifolds for these two irreducible guys. And yeah, this is the complete classification of irreducible quantum flag manifolds. Nothing exciting so far, but it turns out that we have this very pivotal result that for each quantum flag manifold of Hermitian symmetric type, that is for each reducible quantum flag manifold, there exists a unique covariant differential calculus that we denote in this way of classical dimension. This is a result, important result due to Heisenberg call. And as a matter of fact, the differential calculus has all the structures that you can possibly desire. It exhibits a complex structure. It also has a Hodge map and even a non-commutative Kähler structure. And we call the two component omega 10 over GLS and omega 01 the holomorphic and then the holomorphic calculi respectively. Any question? So now we have picked our differential calculus, the homogeneous space that we're studying. And in order to give the statement of the Borel-Weber theorem, we need to understand what are the holomorphic sections. This is a theorem about holomorphic sections, after all. And so we have to go over, and if now I pick a differential calculus over an algebra B, and if I have a left module over B, I can define a connection on F as a linear map which satisfies this generalized version of the Leibniz rule that probably you have already seen. And in the following, we're going to define connections over line modules. So let me also remind you what a line module is. Remember that, or a line bundle. So remember that by Ferez-1 theorem, a non-commutative vector bundle is given by a finitely generated projective module. And line module is just a subcase. In fact, I require a line module over B is an invertible B by module E. That is, there exists another B by module that I call first the dual of E, such that the balanced tensor product of E by its dual and vice versa is isomorphic to B. Now we can finally say what is an holomorphic structure on a vector bundle. This is done by the classical Koszul-Makran's characterization of a holomorphic bundle. That is just the holomorphic version of Ferez-1 theorem. So remember that I can extend any connection to a map from the balanced tensor product of F by the differential calculus. And I can extend in such a way that it is a graded derivation. Then, of course, it makes sense to talk about the curvature of a connection that is just the square of nabla. And the connection is flat if nabla square is identically 0. Then, for an algebra B, a holomorphic vector bundle is given by a pair of a left module F and a connection delta F, which that goes from that goes into the 0,1 component of the complex structure. And if this connection is flat, we call this the holomorphic structure given by del F of F. So an holomorphic structure is a pair F with a connection, with a 0,1 connection. Now we want to give the classification of the line bundle. We want to study the line bundles over a very concrete object, which is our plug manifold. And in the following, I'm giving the characterization of these line bundles. But is there any question before? So, in order to study the line bundles, we can introduce another object, another homogeneous space, which is the Poisson homogeneous space. So classically, the Levy algebra is reductive. It decomposes as the direct sum of a semi-simple part and an abelian algebra. And in the quantum world, this motivates us to consider these objects. So remember how before I consider a set of cross nodes, and I was getting rid of the cross, the E's and the F that corresponded to the cross nodes. Now I get rid of everything. I also get rid of the K that are crossed. And I can consider inside of QG, now I can consider the space of the invariants with respect to this semi-simple component of the Levy algebra. Of course, I am quotienting by a smaller subalgebra of UQ of G. That means that the homogeneous space is going to be bigger than the quantum Flagg manifold. And we call this guy the quantum homogeneous Poisson space associated to S. Okay, so in the case of an irreducible quantum Flagg manifold, okay, so we can also give another characterization of this guy. So in the case of irreducible quantum Flagg manifolds, I remember I always have one cross node, and we let alpha x be the simple root, which is the one that is crossed. We can consider for v of pi x, we can consider with basis, and we can consider and we order it in such a way that Vn is the highest weight vector. Then we can do the same also in the dual basis, but I don't know here if the highest weight covector is the first one or the nth one, but I mean, it's not important at this level. We claim that, and we found that the set of generators of the Poisson homogeneous spaces is given by these two guys. So remember, the elements inside of OQG are given by coordinate functions, and we denote these two particular coordinate functions in this way. I mean, this set of coordinate functions. So why is this relevant? Why are these two objects relevant? Because now I can give another characterization. For any irreducible quantum Flagg manifold, we can introduce the coordinate ring SQRGLS as the subalgebra generated by element Zi. And we define in similar way also the opposite homogeneous coordinate ring. Then, as a matter of fact, both these subalgebras are quadratic algebras, and hence they have a natural grading. We can describe the Poisson homogeneous space of Q of GLS as the quotient of the tensor product of these two coordinate rings by a certain central element of degree 0. This means that I have a grading of the Poisson homogeneous space, and this grading is built in such a way that the degree of the Zi is 1, and the degree of Z minus of Z bar I is -1. So I can now consider the decomposition of the Poisson homogeneous space with respect to this Z grading. And its decomposition is simple object is actually decomposition into line bundles. And moreover, the Poisson homogeneous space is a strongly Z-graded algebra with respect to this decomposition. And this one can ask if there are more line bundles over OQGLS. But turns out that all the line bundles that I can have on the Flagg manifold appears in this decomposition. So this is the complete characterization of the line bundles. And as it was proved by a bunch of people present at this seminar, for each, I mean, this is a simplified version of your theorem, I beg your pardon. For each relative line bundle over over OQGLS, there exists a unique left OQG.
Amiris, why do these exhaust the non-commutative Picard group?
I think the honest answer is that I don't know. So maybe you can add something. Yeah. Yeah, thank you. And this thing stopped working. No. We have a technical problem. So the pointer works, but I'm not able to change the slide. Okay, I will just do it manually, yes. Okay. So we have a unique connection over any relative line bundle, which is also left OQG covariant. No, it's stacked. Okay. Thank you. So as a matter of, for each line bundle K, we gave a construction of this unique connection. And as a matter of fact, we presented this unique connection as an associated connection coming from a principal connection. This is, I guess this could be interesting if you know what I'm talking about, but it's not relevant at this level. And now we know what is our homogeneous space. We know with which differential calculus we are dealing with. We know what are the line bundles. We know all the relative line bundles. We know everything about the connections. So now we have all the ingredients that we need to give the proof of the Borel-Veil theorem. But as a matter of fact, I don't think it's, I should bother you with the actual proof. It's from this point on, it's just some hardcore manipulations that you should, not hardcore, some manipulation that you should make in order to prove the theorem. But let me point out some intermediary result. In order to prove the theorem, you need to prove the Liouville theorem for the reducible quantum Flam manifold. That is, if I consider the 0-1 part of the Heckenberg calculus and I look at the age or at the kernel of the connection into, sorry, at the kernel of the differential into the 0-1 forms. What I get, what I get are only the constant sections. So this is really a non-commutative counterpart of Liouville theorem. And you need this to prove, let me restate the theorem again. You need this to prove the Borel-Veil theorem that now I can state, now I can state knowing all the terms in the theorem. So if I have any reducible quantum Flam manifolds, it holds that H0 of any line bundle EK is isomorphic to, is equal to ZK, where ZK is one distinguished element of the ZI that I presented before, but there, so K is the kth power of one distinguished of the ZI, and if it can be written in this way, it is a reducible UQG model of highest way K var pi of X, where var pi of X is the fundamental weight corresponding to the simple root which describes our quantum flux manifold. And yeah, so we have a correspondence between the representation theory of UQ of G and the holomorphic sections of certain M bundle over the reducible quantum Flam manifold. I guess we got our achievements, and I just have to thank you now.
Questions from the audience or questions from online?
Crossing of nodes procedure. S, or I guess the complement of S, was it? You can be more than one node.
Can be more than one node. Yes.
But Yeah,
So
you were just allowing
here,
one.
if we want to select the flag manifolds, which are also of Hermitian symmetric type, that are the ones for which Heckenberg and Kolb define the calculus. So the ones for which we have a solid theory of differential calculus, we have to cross only one. If you ask for differential calculi for more than one cross, let's say it's a work in progress. Reported about his joint work with Peter.
Right.
And yeah, I'm also doing something.
Thanks.
Rita, did you have a question?
Yes, I do.
Oh, okay.
So, Alessandro, thank you very much for your great talk. I really enjoyed it. Can you go back when you define the ring for the, flag back? Right. No. Right. Yeah. No. It was that. Go back. Go for.
So
right.
This one.
Yes, I really like. Yeah, this one. So so the thing. So I was fascinated by this. You went really fast, saying that you describe OQG mod LS as the quotient of that homogeneous ring by a certain element of degree 0. So I was wondering, is this linked with some determinant type of element? What is this element, this central element?
This element, I think is the determinant. It is the determinant of. Yeah, it's related to the determinant, even though.
Yeah, because I was trying to understand exactly what you're doing, right? Because you need to take this quotient. I don't understand. So it's because
Rita, I remember, and Ray is confirming that this element is related to the determinant, but I can't quite remember how it is constructed.
Because is it maybe, it is I'm guessing, is it related to the fact that there is this central thing in the levy? Maybe this is it, Ramon?
Yes, it's related to the
It's because of it. Okay.
Yes, absolutely. I will send you the exact reference. It's in Heckenberg and Kolb also, I think. So
yes,
I can send you the exact reference with the page and everything. Yeah.
So I'm a little, why do you need both? Because you need Z and Z bar. This is the reason, right? You need both the S and
yes, this is the reason.
Exactly. So you're looking at the real form, so to speak.
Yeah. Yes, if I got both of them, I got both positive and negative line bundles.
Yeah, I was wishing you were going to in more technical detail because, Alessandro, I know this, but I understand also that you could not. But thank you so much. I enjoyed it. Thank you.
Thank you. Thank you, Rita. Yeah, when
It's from online. No raised hands. Oh, okay. Well, if not, then we'll thank Ali again.
Ramon, are you there?
All right, third microphone. Okay, so next week, we will, on the 8th of March, we will have Andrew Stocker of the University of Colorado Boulder, and he will speak about synchronizing dynamical systems. And this will be an online talk. So, okay, thank you and see you in next week.